All right, so we're going to continue our discussion for topic 6, and we're going to move into discussing space trusses. So we're still talking about structural analysis here, and we're going to shift from talking about 2D systems now to 3D trusses, which we also call space trusses. So just like for 2D systems, we have a few assumptions that we have to make before we're able to structurally analyze these systems. A couple of these assumptions for design and for analysis actually are that two force members are present if loading is applied at the joints, and we know for trusses that we are applying all of our loadings at the joints, so this is valid, and that each joint resists translation in 3 directions. So if you remember, for 2D systems, each joint resisted translation in 2 directions, in the X and the Y direction, and that's kind of the definition of a pin. So all the members are pin connected. That assumption extends to 3D truss systems, but now, of course, since we have one more dimension, translation is resisted in the X direction here, whoops, in the Y direction, and in the Z direction. Okay, so let's go ahead and jump into an example. We're going to use vector analysis to solve for what's happening in this truss here, and also some of the previous methods that we discussed, method of joint, method of sections, to solve for what's going on. The only difference really is that we now have a third equation of equilibrium to deal with when we're using method of joints. Because if you remember, for 2D systems, we only had summation of forces in the X and summation of forces in the Y. But now for method of joints for space trusses, we have summation of forces in the X, summation of forces in the Y, and now we have summation of forces in the Z, of course. Okay. So the first thing I'm going to do here, let's read what's happening. We want to determine the forces acting in the members of the space truss shown, and we want to indicate whether the members are in tension or compression. So we have a lot of stuff going on in this image here. What we're going to do is we're going to break it up per joint. So we're going to apply something similar to the method of joints here to solve this problem. And I'm going to start by analyzing joint A. So I'm going to go ahead and I'm going to isolate joint A, and then I'm going to draw all of the members and forces that are coming out of joint A. Okay. The first thing actually I'm going to do, I'm going to draw the coordinate axes just like they're drawn on the image. So basically the X, Y, and Z. X is kind of coming out like this, and Y is in this direction positive, this direction negative. So here is our Y, our Z, and our X is kind of coming out here. Okay, now I'm going to go ahead and draw the forces that are acting at point A. So purely along the Y direction, I have FAB, the force in member AB, right? And I also have, this is at point A right here on the system, so I just counted for point A, FAB. I also have this force here, which I'm going to call FAE because it's going towards joint E. So I'm just going to kind of draw that in this direction since it's not purely in any coordinate direction. FAE. I have FAC purely in the negative Z direction. And then I also have a 4 kilonewton load on joint A, or at joint A, and it's purely in the negative Y direction. Right? I think that's it. We've accounted for everything. So one of the reasons I picked joint A here is because we have 3 unknowns. Right? We have 3 unknowns, 1, 2, and 3. And we know that for method of joints with 3D systems with space trusses, we have 3 equations. We have summation of forces in the X, summation of forces in the Y, and summation of forces in the Z. So we're good to go in solving for this. Now, one thing I'm going to do before I go ahead and tackle this problem right here and solve for what's happening at joint A using equilibrium, I'm going to go ahead and put the force P, the force AB, AC, and AE from this diagram and this diagram here Actually, let me show it from here. I'm going to put it into vector notation. So this force P, the P equals 4 kilonewtons, this one right here, I drew it in red. That force P, if I want to write this in vector notation, we know that it's acting in the negative direction because it's in the negative y direction, right? Y is the j direction, and we know that this is all in kilonewtons. So that's how I can write this in vector notation. FAB in vector notation is just the magnitude of AB, and that's purely in the j direction, the y direction, right? FAC is equal to negative FAC, and that is acting in the k direction, negative because it's in the negative k direction, opposite of what we've defined as positive z. And then the last one here that's a little bit, right, it's acting in more than one direction, it's a little more difficult to see, would be FAE. And that's going to be equal to the magnitude of FAE times the position vector from A to E divided by the magnitude of the position vector. And we can actually get the position vector of going from A to E. So let's work on this right here. Let's work on solving for the position vector from A to E. And let's do this on this diagram right here. So we want to go from point A to point E. So that means we're going to have to travel. If you guys see here, this is we have 2 here, right? We have 2 going in this direction. We have 2 going in this direction. So that would put us at a 1, 1, root 2 triangle, right? Or 2, 2, and then 2, root 2. Okay, so this would just be a 45-degree, 1, 1, root 2. So my position vector, I'd have to travel that diagonal on the I along the x direction to get to point E. So along the I would have to travel 0.577 along the I. Okay, but then I'd have to travel another positive 0.577 along the J, and then the same but in the opposite direction, 577 along the K. Okay, so I can plug this in and I get FAE, the magnitude of FAE, times 0.577 along the I plus 0.577 along the J minus 0.577 along the K. Now I can go ahead and I can apply equilibrium at joint A here. So I'm actually going to copy this down here. And I'm going to go ahead and apply equilibrium at joint A. So let's start with, well, equilibrium, right? We're going to do sum of all the forces equals 0. So if I want to put this all into one large system of equilibrium, I can very easily say, well, then I have force P plus FAB, vector AB, plus vector AC, plus the force vector AE, and all of that has to equal 0. And I can actually go ahead and plug everything in directly as long as I keep the IJK notation. So I'm going to go ahead and plug all that in. Now what I can do, I'm going to go ahead and highlight here. So let's highlight all the I's. That's pretty much the only I have. We'll use green here for the J's. And we'll use blue for the K. And now we can separate those 3 terms. So we can say sum of forces in the x direction have to be 0. And I pretty much just have the yellow highlighted portion. So I get FAE is equal to 0. Okay. Pretty simple. Let's do the same thing with y and set that equal to 0. I have -4 plus FAB plus 0.577 FAE equals 0. And I can't solve for anything there because I have two unknowns, so I'm going to go ahead and apply my third equation of equilibrium. And I get negative FAC minus 0.577 FAE equals 0. And I know that FAE is 0, so if I plug in a 0 here, I end up getting FAC is 0. So I also can solve for FAC is equal to 0. And then if I plug this back in, I get FAB is equal to 4 kilonewtons, and this is positive, so it's in tension. And these are my final answers for joint A. I ran out of room here, so let me add a page. This is 28. Okay, we still need to analyze joint B though, because we want to solve for all of the forces in this system, not just the ones at joint A. Okay, so we're going to continue here. We're going to go ahead and do the same thing for joint B. Okay, so here I'm going to draw joint B. I'm going to go ahead and draw the coordinate axes again. And just for your reference, you can choose any directions to be the positive, positive X, Y, and Z. I'm going to go ahead and keep what we had earlier. Just drawing that negative direction too, because I had a force on that negative direction, so it was kind of easy to see. So I'm going to draw it, but remember, whichever direction I have the arrow in, that's the positive. Okay, so I have 4 kilonewtons acting in this direction. This is that force, remember, FAB, that I already solved for. Right? I have 2 kilonewtons pushing down at joint B. This is joint B. I forgot to write it here. And then I have 3 unknown forces. I have FBE. I have FBD. And I have FCB as well. So I want to show you all here that you can assume any direction is positive for these forces and the work will correct itself. So even if you were to assume, let's say one of these forces is going in this direction, let's call this FCB. I'm going to show you how it doesn't matter which direction you assume. The equilibrium functions and equations will correct your work. Okay, so I'm going to show you that right now. So let's do sum of forces in the x direction is equal to 0. I would have just the component of FBE, right? I'd have just this component of FBE. And I would have the 1 over root 2, because again, I have those 45-degree triangles, okay? This is going to be very straightforward here. Sum of forces in the y is equal to 0. I have the -4 kilonewtons plus the component FCB times 1 over root 2. And then I have sum of forces in the z direction. This is where I'm going to have most of the work. So I have a -2 from the 2 kilonewton force plus the FBD, which acts directly in the z direction, minus FBE, which has a 1 over root 2 component in the z direction, plus an FBE, which also has a 1 over root 2 component in the z direction in the positive z. That's all going to be 0. And if I solve for these 3 equations, I get FBE equals 0. I get FCB equals 5.65 kilonewtons in compression, and I get FBD equals 2 kilonewtons in tension. Now, this is what I wanted to show you about picking the direction. So I got a positive value here, but that's because I drew it, the force going into the joint in compression. If I had drawn it the other direction, I would have gotten a negative, which means I assumed incorrectly, which means it needs to be going into the joint. So no matter how you draw it, you'll always get the right answer if you just keep track of your signs. Okay? Now, at this point, if you apply scalar equations of equilibrium to the forces acting on the free body diagram of joints D and C. So I want you guys to try this. You'll get FDE equals FDC equals FCE equals 0. There we go. So how did we get this? All you have to do is go back to the original FBD, go back to our original problem here. And now vector analysis doesn't need to be applied because we've already solved for so many of these forces. Just apply scalar equations of equilibrium. Okay, at joints D and C. So isolate D and C, apply the scalar equations, and you will solve for all of these to be 0 as well. Okay. Okay, so we're going to move on to discuss frames and machines now, and how we can apply some similar methods and concepts that we've been learning so far from trusses to analyze different types of structural systems. Okay, so two of those types of structural systems are frames and machines. So if you are a civil engineer, you'll be dealing more with frames, and if you're a mechanical engineer, you'll be dealing more with machines. But depending on the type of job you get in industry, you could be dealing with a combination of both of these things. So they're both very useful and very commonly seen in practice. Okay, I have two pictures or images here that show you what frames and machines are, or these are just two examples, but there are hundreds of thousands of different types of examples of these. So we're gonna go over a couple of these when we're going through our in-class examples, but here we have a crane that's shown in a real world application, and this is a typical example of framework. So this would be a frame, and you could see this is obviously a 3D system because this exists in the real world. We can analyze frames as 2D systems or as 3D systems. Okay, here is just a common tool that you would see in kind of an everyday toolbox, like pliers, right? Pliers are a type of machine. This is a very simple machine. It's not a complex machine. But this is an example because what's happening here is we apply force on the handles, and then that creates a much larger force at the jaws, which allows us to perform operations that we couldn't necessarily do with our hand. So we're able to basically distribute force with machines and accomplish tasks that we wouldn't have been able to do without those machines. So we're going to go ahead, we're going to continue this discussion, and we're going to go through a couple of examples of both frames and machines and see how we can use concepts of structural analysis to analyze and actually design both of these systems. So some important things we need to know about frames and machines: they're often composed of pin-connected multi-force members. And I should say with this, when I say they're often composed or designed, they're often also assumed to be pin connected, because one thing that we've noticed so far, or I hope you've noticed so far, is that a lot of times the way we can analytically approach a situation and take it from a real world model to an analytical model is by making these assumptions. So one of the assumptions we make often when we're dealing with frames and machines is that those frames and machines are connected through pin connected members, which, remember, means that if it is a 2D system, you're only resisting translation in both directions, where if it's a 3D system, you're resisting translation in all three directions. That system is allowed to rotate at that point. Okay, and we also have multi-force members. Frames, the primary purpose of a frame is to support loads. If you're sitting inside of a building right now, or if you're sitting outside and you can see a building in front of you, that building consists of frames. So one very common type of frame that you see in structural analyses is a frame that looks like this. It consists of columns and beams. And this is just a one bay frame. We call this one bay, B-A-Y. However, you'll have multiple bays, especially depending on how large your building is. Okay, and you'll have multiple columns, you'll have multiple beams connecting, you'll have a floor, roof system connecting all this, but this is what we call a frame. Okay, now machines contain moving parts, and they're designed to transmit and alter the effect of forces. So just like we use that example of pliers, where your hand does not necessarily have enough force to accomplish the task you're trying to get to, by pushing in those two, the bottom of the pliers, you're basically transferring the force to the jaws and allowing it to perform the action that you couldn't do with just your fingers or your hands alone. Okay, again, this is a very simple concept. We're going to extend this to some more advanced concepts in our examples. Okay, most frames and machines can be solved for using equations of equilibrium. And I'm going to define what this sentence means now. You'll hear this a lot in your future classes. This is a concept called a determinant system. I wrote it right here. I'm going to write it again. Okay. The opposite of a determinant system is an indeterminate system. I would just put an indeterminate. That means you cannot solve for the system using only equations of equilibrium. Okay. I get a lot of questions about this sometimes, like what do we do if we have an indeterminate system? Well, you can still solve for it. It doesn't mean that you can't build that in the real world. It doesn't mean that you can't solve for what's going on. We are advanced enough and we have capabilities to solve for these systems. And they're pretty straightforward and quite simple depending on how complex the system is. All that it means is you cannot just rely on equations of equilibrium to solve for it. Okay, we're not quite there yet in this class to learn how to deal with indeterminate systems, but you will spend, if you're in civil engineering, you will spend most of structural analysis figuring out how to solve for these problems, how to solve for these indeterminate systems. Okay. All right. And so if I haven't made this clear yet, just so I make it very clear, in this class, we will focus primarily on determinate systems. Okay. You'll see some indeterminate systems starting in mechanics of materials, and then in structures we'll have a large focus. All right, so let's go ahead and jump into an example here. Our first example is a simple frame, and what we want to do is we want to draw the free body diagram of the entire frame, including the pulleys and cords, the frame without the pulleys and cords, and each of the pulleys. Okay, the reason we want to do this 3 different times is because I don't want to have to do this every time we solve a problem. I want us to all be able to recognize when and where to make these cuts when we're drawing our FBD. And this is kind of where that critical thinking aspect comes into it. You always want to try to make your life easier when you're solving problems and not more complex. So what I mean by that is don't expose extra forces that don't need to be exposed. Okay, and you'll kind of see what I mean by that as we go through part A, B, and C of this, okay? So let's start here. Actually, I'm going to erase this. I'm going to start down here. No. How much? Okay. Let's see. Part A. So let's do part A, the entire frame. And I'm going to draw this system again right here so we can see how we would draw this from scratch, okay? So I'm going to draw a line representing the longitudinal member going from the pin at A to the pulley at B. So here is my pin at A, here is my pulley at B, and I'm actually going to draw that pulley. Okay, something like that. Pulley at point B. Okay, and I also have another member, a transverse member pushing out like this, and I have a pulley at that point as well. And this is point C. This is the pulley at point C. And that pretty much is the whole structure there. That's the whole entire structure. But now I need to draw the FBD, the free body. This is just the system. I need to draw the forces acting at these points. So, oh, I missed this little transverse member as well. There we go. And then I should draw the chords here. Even though we're going to draw them as forces, it'll help us to kind of see what's going on. We have a chord there. We have a chord here. Right, okay. And I'm just going to go ahead and directly draw these forces here. So this chord, this is 75 pounds. We have this tension here from this chord. We have an unknown tension here, T. We don't know what that is. We have to solve for that. And then at A, we have a pin. So of course for pins, we have 2 forces, one in the horizontal direction, one in the vertical direction. Okay. Now the interactions at the points where the pulleys and the cords are connected, they become basically internal forces which cancel out. They become these pairs of internal forces which cancel out. Okay, that's why we don't need to actually draw what's happening internally. And there was a problem that we did in a previous example in this class where I showed you that. So we don't actually need to expose what's happening at the pulleys. I'm going to show you that in part C because it's saying draw the FBD of each pulley. But the reason we don't actually need it to solve what's going on is because those pairs of forces actually cancel out. Okay, but that's all we want. We want the FBD of the entire frame. Let's move along and do part B, which is, let's see, the frame without the pulleys and cords. Okay, so if we don't have the pulleys and cords, we would have the frame like this. And I have this transverse member here, another transverse member here. I'm not going to draw the pulleys anymore because we're removing the pulleys. We're exposing what's behind the pulleys. So I did have a pulley here and I did have a pulley here. If I take the pulley out, well, I have to draw my reaction, whatever's keeping that pulley in place. I have a pin at the middle. So I would have a pin reaction there. I still have the 75 pounds of tension. And then of course I'd have a CX and a CY from the pulley at C. And I'd have some tension force in this direction. And then I'd have an AX and an AY. Okay, so for your reference, we don't typically draw free body diagrams like this because look how much more complex this FBD at in section B is versus what we drew in section A, which is much more straightforward. Section A here, we only had 3 unknown forces. Here, we have 1, 2, 3, 4, 5, 6, 7. Right, 7 unknowns. That's not very fun. Nobody wants to deal with more unknowns, right? Okay. So the last part of this, part C, is just the pulleys. So we're going to go ahead and isolate just the pulleys and see what's going on here. Right? We have the 2 pulleys. Well, the pulley at B, we know we have 75 pounds in tension here, which means that we have 75 pounds in tension here. It's the same rope. And then, of course, we have the pin. You always have a pin at the pulleys, but obviously it's your choice to expose those pin forces or to keep them connected like this. Okay. And that's pretty much all we see. And for C, this is B and this is C. For C, we don't know what the tension is, but whatever that tension is, it's the same tension in the whole cord. And then we have CX, and then we have a CY, right? And the BX, BY, CX, and CY of the pins on the pulleys are equal but opposite forces, right? They're opposite to the force components exerted by the pins on the frame. So they're equal and opposite to, I'm going to re-highlight these. So these here are equal and opposite to these here. And these here are equal and opposite to these. So you'd have to do way more analysis. You'd have to analyze both of these systems here to just get what you could have gotten from just looking at the entire frame. So sometimes you do have to strategically think about what you want to analyze before you kind of jump into the problem. And once you can get this free body diagram in the most simplest form, and then you analyze the problem, that's really how you can approach the problem in the most simplistic way and the most straightforward way. Okay? Okay, let's continue. We have another frame here, and now we want to actually do some analysis on this frame, so we're going to move past just drawing free body diagrams, and we're going to determine the horizontal and vertical components of the reaction at A and the force at C. Okay, so of course our first step here is always to draw our FBD. So I'm actually going to first, let's see what we'll do here. There's a lot of stuff going on. So let's draw the FBD of this cylinder system and see what's happening. Okay, so I have a pulley here, and I have this cord, this tension cable kind of that's going through this way. And I have some T, but I know I have this cylinder at the bottom, and this cylinder is 50 kilograms. That was given in the problem right here, 50 kilogram cylinder. And that would mean this is 50 G, the weight of that system, right? Well, that means if this is 50 G, this is 50 G. And if this is 50 G, then T is 50 G. So we know what T is. And then of course, if we're isolating the pulley, we also have the force of the pulley, of the pin. Okay, and we can actually pretty easily solve for what's going on here. We can say the sum of forces in the x direction are equal to 0. This direction is considered positive. I would have dx minus 50 times 9.81 equals 0. And I could solve for dx as 490.5 newtons. I can do the same thing and apply equilibrium in the y direction, say up is positive. I get dy minus 50 times 9.81 equals 0, and I get dy is 490.5 newtons. The same thing, right? Because I have the 50G in both directions, basically. Okay, so let's go ahead and highlight our results here so we can keep this organized. Okay, now let's move on. We have one part of this kind of solved for. Let's continue to pick this apart. And we're kind of using the same concepts that we used for truss analysis, where we're just kind of walking ourselves through the system and trying to solve for the forces, right? This is very similar to method of joints, okay? What I'm going to do now, I'm going to draw another FBD. So I'm going to call this like FBD1. Let's draw another FBD here. Let's see what else we can pick apart. Okay, so I'm going to isolate the system FBC, this member here, BC, and kind of see what's going on at that point. Okay, so let's go ahead. Let me draw the member like this. Okay, I also have this member here in this direction, right? And this is my point A. Actually, this we'll say is my point D here, where everything kind of connects. Let me see if I can draw this a little better here. This here where these would, I'm breaking it up, but just to show you where they connect, this is point D up there. I'm redrawing this whole system here. And then we have our point B right here. So if we're trying to expose all these forces in the system here, what we have is we'd have this pin, right? We'd have this pin dx dy here. And what we have here is we have a two-force member, right? We have this two-force member, BC, okay? So I'm going to draw the member here. I'm going to draw FBC here. But if we also show what's happening along the member here, if we isolate just the member, we basically have this two-force member look something like this, where it's experiencing just this one force that goes through it. Okay? So this is a two-force member. All right, so let's continue and let's see what we can solve from equilibrium through this system. So I'm going to do the exact same thing. I'm going to start here by, I have these three equations of equilibrium, right? Because this system is not just isolated at a joint, so I can actually use moments. So if we remember, oh, I forgot the pin reaction at A, though. I forgot this. A is a pin, right? So I have an AX and I have an AY. Okay. So I'm just going to look right now. Let me erase this so I can make this a little more clear. I'm just going to look right now at this guy. Okay. And I'm going to sum the moments about point A and set that all equal to 0. Say this direction is positive. I would have FBC times the moment arm of 0.6 plus 490.5 times the moment arm of 0.9 minus 490.5 times the moment arm of 1.2, and that would be 0, equal to 0. And I can directly solve for FBC as 245.25 newtons. I'm going to move this down so I have a little more room. I'm going to continue to apply equations of equilibrium to solve here. I'm going to say this direction is positive. I would have my AX minus 245, which I just solved for here, 0.25, minus 490.5. Where is the 490.5 coming from? Well, that's dx and dy. I'm just plugging those in. Okay, and I can directly solve for AX here, 736 newtons. And then I can sum forces in the y direction, set those equal to 0, and I get AY minus dy, 490.5 equals 0, and I get AY is 490.5 newtons. So I was able to solve for FBC, AX, and AY here. So all this took was kind of strategically pulling apart the problem. And what I like to the advice I like to give whenever anybody's having trouble with solving these problems is this is really a trial and error process. So if you isolate part of the system and you can't solve for what's going on, that is totally fine. You'll really quickly realize you have more unknowns than you're able to solve for. And really the best way of figuring out how to solve these problems is by continuously doing example problems and working on these example problems. The more you do, the more second nature it will become for you to really understand how to solve these problems. And again, I do mention this in class often, and I'll say it again in this video. Hopefully you guys are listening and not fast forwarding this part. But you have to make sure that when you're testing yourself, if you want to prepare for the exam, you are trying to solve these problems without looking at the solution. That is essential to helping your brain develop those critical thinking skills. Okay, so please try doing this on your own time. Make sure that you're able to recreate this solution and solve for this problem without looking at my solution, and then check your work afterwards. And if you're still having trouble, then please, of course, approach me and we can work on it together, okay? All right, let's go ahead, try another frame example here. We're going to try a lot of examples because, again, doing a lot of examples is what's going to really ingrain this into kind of your mind, okay? So, for example 9 here, we want to determine the horizontal and vertical components of force which the pin at C exerts on member BC of the frame. So we basically just want the components of the force of the pin, okay? We want to know what all these pin forces are, okay? So what we're going to do here is I'm going to do this two different ways, okay? I want to show you all that even if you don't recognize something as a two-force member or you approach it in a different way, there are multiple ways to solve this problem. So person X might solve it in a different way than person Y solves it. That is totally fine. You might have a different approach than I have, and that's just part of the process of this. There's a lot of different ways to solve these problems. So what I want you to do is maybe stop this video here and try solving this on your own. I want to see if maybe you come up with something more like solution 1 that I'm going to show you or solution 2 that I show you. Okay, so go ahead and pause this video if you'd like. Try solving this on your own. and then you can continue watching it. Okay, so I hope you all tried to solve this problem. Let's go ahead and go through it. I'm again going to try this two different ways, or to show you two different ways here. So I'm going to call this solution number 1. You'll see the difference when we go over solution 2. Okay, so solution 1 is if you were able to recognize that AB is a two-force member. I don't have any other forces acting on AB, I just have that pin. And I have B, which also has this internal pin. So what happens is the resultant of the pin here and the resultant of the pin here are the same force because there's nothing else acting on the system. So if I were to isolate that member, whatever the resultant of the pin at B is, that's the same thing that I have here. Oops, these are not in the right directions. And then really that translates to the next part of the frame here, of course, right? This is equal and opposite. So if I have FAB at this point here, then at point, this is right, this is point A, point B, point C. I would also have an equal and opposite FAB here. And then of course I have the rest of my member. I have CX, I have CY. BC is not a two-force member because I do have this load here of 2,000 newtons. I just have to solve for what's going on there. So this is solution 1. If you were able to recognize this, basically, I'm going to, again, go over a solution where that's totally fine if you didn't see that. It's totally fine. Okay, it's a little more work, but not a big deal. Okay, so all I'd have to do here, I'm actually going to go ahead and just analyze this part of the system because I don't really need to do anything with the other part. I can go right ahead and I can say, okay, I'm going to sum moments about point C and set that equal to 0. And I would get the 2,000 Newton force times a moment arm of 2 minus FAB sine 60 times a moment arm of 4 equals 0. And I can really easily solve for FAB is equal to 1154.7 newtons. Okay, and then I can continue and apply the rest of the equations of equilibrium. I have sum of f of x equals 0. This direction is positive. I get 1154.7 cosine 60, the 60-degree angle, minus cx equals 0. I get cx equals 577 newtons. And my last equation of equilibrium, sum of forces in the y are equal to 0. I get 1154.7 sine 60 minus the 2,000 Newton force plus cy equals 0. And I get cy is 1,000 newtons. So with 3 equations, 1 FBD, I was able to solve for everything just by kind of recognizing that that was a two-force member. AB was a two-force member. Okay. All right. So now again, I'm going to go through another solution here, and I'm going to show you how it's totally fine, again, if you did not recognize that AB was a two-force member. Even sometimes when I'm solving these problems, I don't solve them recognizing that it's a two-force member, and that's totally okay. So we're going to kind of pull down here and go over solution number 2. And on an exam, you're free to solve this however you like. Of course, if you recognize it, it's a little bit of a quicker solution. So if you're pressed for time, you might really want to study these. But again, I'm not going to mind if you solve this either way, as long as you're getting the right answer or the right approach. So I'm going to draw the FBD of the whole system one more time. Okay, so here we have point A, point B, and point C. So I like to call this exploding the system so we can expose all of the forces. That's why I'm not connecting point B. I want to explode it so I can see what's going on here. So here at A, I have the pin AXAY. At B, I have another pin BX, BY. And then I have equal and opposite forces, where I still have a By here. I have the Bx here. Okay. I have the 2000 Newton force. And I have Cx and Cy. So you may already have noticed that I need to do two analyses here. I have how many unknowns? Let's go through and highlight. 1, 2, 3, 4, 5, 6 unknowns. But I only have 3 equations of equilibrium per structural system. So I need to analyze both of these systems. I need to analyze this system with my equations of equilibrium, and I need to analyze this system using my equations of equilibrium. Okay, so let's go ahead and do that. Let's start with member AB. Which is this member right here. AB, BC. Okay, so we're going to do this 6 times, apply 6 equations of equilibrium, 3 for each section. Start with MA is equal to 0. Counterclockwise is positive. And to be honest, you can do this pretty quickly. It shouldn't take too much time if you are kind of getting the hang of these summations and you've been following along throughout the rest of the class. These should be really quick now. Okay, that's one equation. Summation of fx equals 0. This should be getting really monotonous for everybody. I'm just going to go through and get all the equations down, and then we'll worry about solving them using algebra. And that's all I can do for AB. I'm going to go ahead and do the same thing for member BC. And I'm going to start by summing moments about the pin C. You can start at B as well. It doesn't matter. Go ahead and sum forces in the X equal to 0. Bx minus Cx is equal to 0. And I'm going to sum forces in the Y, set that equal to 0. This was this direction positive, this direction positive. I get By minus 2000 plus Cy is equal to 0. Okay, now let's go through. I have 1 equation, 2, 3, 4, 5, 6. 6 equations and 6 unknowns. So what I'm going to do, I'm going to go 4, 1, 5, and 6. So a lot of these are pretty simple, like AY equals BY. So if you go 4, 5, 1, and 6 and combine all of these, you will get By equals 1,000 newtons. Bx equals 577 newtons. Cx is equal to 577 newtons. And Cy equals 1,000 newtons. Okay, so they're the same answers we previously got in this method. Either method you choose, you should get the same answer as long as you are theoretically sound in the way that you're setting everything up. Okay, so now for example 10, we're going to analyze a compound beam that is pin connected at B. And this is a really important example because we haven't dealt with a beam that has 2 parts to it where we have an internal pin at a point. So whenever we have an internal pin, an internal pin is actually also called a hinge. Okay, so you can use either of those words to describe what's happening at point B here. But the way you can kind of think of an internal pin or a hinge is exactly the same way where if you were to look at a door in a door frame, you would see the hinges of the door allowing for rotation around one axis, but not allowing for translational movement. So you want to analyze an internal pin or a hinge as the same way, where we allow rotation at that point, but no translation is allowed. Okay, And just by looking at this system here, if I were to draw the FBD, let's go ahead and do that. I have a fixed support at A, which means that I have three reactions here at A. I have an AX, I have an AY, and I have a moment, which means I can't rotate and I can't translate, okay? I also have CY here. So if I don't want to break up the system, right away I can see I have four unknowns. But I only have three equations of equilibrium. That is not a good looking three. Let's try that again. Three equations of equilibrium to use, right? So this isn't going to work. I can't solve for four unknowns with three equations. So what I have to do is I have to split the structure up. Okay, so I'm going to draw the FBD of both of these systems. I'm going to split the structure up with AB and then BC. The internal hinge actually helps us in solving the problem. It helps us create two structures from one, which gives us an extra set of three equations to use at our disposal. Let me show you what I mean by that. So I'm going to separate this into part AB and part BC. And again, I like to call this exploding the structure and kind of exposing all of those unknowns, right? So here again, I'm going to redraw these. We have an AX, an AY, and we have an MA. We also have a BX, we have a BY, and we have a 10 kilonewton load on this system. And that acts at 2 meters away and 2 meters away. And it is a 3, 4, 5 triangle. And for BC, we have equal and opposite reactions of the pin here. So we have BX, and if I drew BY going down on one side, I need to draw BY going up on the other side because they're equal and opposite, okay? I have an 8 kilonewton load acting directly in the downward direction. That is from the 4 kilonewton per meter, right? Because the resultant here would just be 4 times 2 equals 8. So I'm just going to draw 8. And from BC, that would just be 1 meter away. And then, of course, I still have that roller at C, so I'm going to draw CY, which is the roller reaction. Now what I can do is I'm going to choose, so I'm going to actually highlight both of these. This is one part of the structure that I have to analyze, and this is the other part of the structure I have to analyze, okay? So I'm going to start with BC, okay? I'm going to start analyzing the section BC, and really quickly we can see when I sum forces in the x direction, set that equal to 0, say this direction is positive, I get BX is equal to 0. I'm now going to sum moments about the pin, set that equal to 0, and I get -8 times a moment arm of 1 plus CY times a moment arm of 2. That's equal to 0. And I can sum forces in the y direction and set that equal to 0, say up is positive, and I get BY minus 8 plus CY equals 0. Okay, I do need to also look at the other direction before I can really solve for anything here. Okay, so I'm going to go ahead and now look at AB. So this is AB, this is BC, right? Just so we know. I'm going to do the same thing. I'm going to apply the equations of equilibrium here. This direction is positive. I have AX minus the component 3/5 of the 10 kilonewton force plus BX equals 0. I can sum moments about the pin, point A, set that equal to 0. Counterclockwise is positive. I have a moment at A minus the 10 times 4/5 component times a moment arm of 2 minus BY times a moment arm of 4, set that equal to 0. And I can sum forces in the y direction, set all those equal to 0. And I would get AY minus 10 times 4/5 minus BY equals 0. And I basically have these 6 equations, right? Well, I already solved for one of them here. 2, 3, 4, 5, 6. And then using algebra, you can solve for all of these unknowns and you should get the following. 6 kilonewtons. We already solved for Bx equals 0. Cy is 4 kilonewtons. Ay equals 12 kilonewtons. By is 4 kilonewtons. And Ma is 32 kilonewton meters. And that's it. All we had to do is split up the system at the hinge, and that's actually a technique to make a system that is indeterminate determinate, because before we could not solve for the system without splitting it up at point B. The minute we split it up at point B, it becomes solvable because we increase the number of equations we have due to equilibrium at our disposal. Okay. Let's go ahead and do the last example of this topic, example 11. We have a frame here, and we want to determine the horizontal and vertical components of the force that pins A and B exert on the frame. So we basically just want the reactions of both pins. Okay, so let's go ahead and draw the FBD of the system. Draw over here to the side. We have a pin at A. We have a pin at B. We have an 8 kilonewton resultant force. And we also have an internal pin at C. So for now, we'll just write this as A, B, and C. And this here is 4 meters. And this here is 3 meters. Okay. Now you might have recognized this, but we do have a 2-force member here. This member AC, right? This is a 2-force member. Okay, so let's do this. Let's separate this and analyze these systems. So let's do member BC. Let's draw what's happening with member BC here. So for member BC, we have Bx, By. Since this is a 2-force member, at C, we just have some resultant that pin exerts, FAC, right? Some resultant of that pin at C, and we have 8 kilonewtons. But then the pin, if we look at that pin AC, we can see we have that force FAC back on the pin, right? And we also have this AX and AY. Okay. So we can actually analyze both of these systems. And once again, I urge you all to try this without recognizing that we have a 2-force member. You can absolutely still solve for what's going on. This is just one possible solution here. So you guys should try this without recognizing that it's a 2-force member and see what you get, okay? Now I'm going to continue drawing this line down, separate the analysis. And on this side here on the left, I'm going to do member BC, and then on the right, I'm going to do AC. So here, let's sum moments about point B, set that equal to 0, assume counterclockwise is positive. We have the 2 times the 4, which is the 8, that 8 kilonewton resultant, times a moment arm of 2, minus the component FAC times 3 over 5 times 4. And we're going to set that equal to 0, and we can directly solve for FAC as 6.67 kilonewtons. If we go ahead and sum moments about point C now, and assume counterclockwise is positive, we can directly solve for Bx. Bx times a moment arm of 4 minus that 8 kilonewton resultant times a moment arm of 2 equals 0, and we get actually Bx equals 4. Okay, and if we use our last equation, we have one more to utilize. Up is positive. We see that 6.67, which is FAC, but the 4 over 5 component of the force, minus By equals 0, and we get By equals 5.33 kilonewtons. And on this side, we're going to analyze pin AC. So I have some room up here. I'm going to actually just do it up here. I have sum of forces in the X. And remember, because this is method of joints, technically, I only have those 2 equations of equilibrium to use now. the 3/5 component here, and I can directly solve for AX, which is 4 kilonewtons. And then I can sum forces in the Y direction. Up is positive, and I get AY minus 6.67, but the 4/5 component, which is in the up-down direction, and I can directly solve for AY as 5.33 kilonewtons, and that is my answer. So I have AX component, the AY component, and I have the BX component and the BY component, which you'll see are the same, right? Okay, so that concludes topic 6, which was structural analysis.